Okay, so I will give you a brief intro on first Fourier FFT, Fourier transform actually. FFT we will not discuss, but how it is done and de-aliasing. I think it's interesting how it is done. So I will just briefly explain that. Now, so we will do discrete Fourier transform. So both real space and Fourier space are discrete. Now, if you recall, in our lectures, x was real, but k was discrete, right? But in simulation, both x and k are discrete. In computer, discrete. Okay, I mean, there sometimes we can make continuous, but essentially discrete. So D for discrete. So R was real, but I will make it discrete. I will illustrate using 1D. So all this discussion, future discussion will be 1D. So in 1D, this becomes fx is this sum, right? Now x is, so I am going to show you this one, and so this is before. So fk is 1 by integral. Okay, this is how we computed. So fx is real. So this is integral. Now if I discretize in the following way, so we have this 1D line 0 to L is periodic. So you do not save both the points. So if there is a constraint, then you do not save both, you keep only one, because you keep both, then you have to satisfy the periodic boundary condition. So you keep you do not save this, just save point to the left of it. So J is my, these are grids, J is my grid index. So I have n points, so I can write my xj is j L by n, 0 to n minus 1, not n. N will include the last point, so just n minus 1. And this is nice in Python and C. Okay, so it starts from 0, and k is 2 pi by L k bar, and this is integer. Takes both negative and positive values. So this kx, what happens to kx? K bar will be, I think I discussed that in the last lecture, minus n by 2 plus 1 to n by 2, and kx is, so multiply this, my L will cancel, right, this L will cancel, and we get 2 pi, I forgot, 2 pi j k bar by n, fine. Now, so what is, now by the way, this dx will become, so what is dx? So xj minus xj minus 1, which is L by n. Okay, so LL will cancel, so it becomes 1 by n. So this thing becomes 1 by n and sum. Okay, so there is a j missing here, j. So this is called DFT, discrete Fourier transform. So given fj at all points, I can compute fk, this Fourier transform, or given fk, I can compute fj. So this is called forward transform, and this is called inverse. And we stick to, I stick to my notation, k is Fourier and j is real. And there is a reasonably good manual called FFTW, fastest Fourier transform in West. So if you look at their website, you will find some more details. Now this will take, as I said, it will take, given n points, it will take n squared. If I just do by ordinary, so this, what is expensive? This is sum as well as multiplication. So the multiplication here of this exponential and this. Of course, computing exponential is also, it is done live, it is not saved in a data, saved in array. Exponential is computed live, and so there is a multiplication, computation exponential, and there is a sum. So how many sums and how many multiplications are there? So for every j, I need to compute n times, and there are n j's, so it becomes n squared in 1D. In 3D, this is easily generalizable. So is m squared, m is number of points. but this idea of FFT is, in fact, let me just make one line remark. So, we have this data which is 0 to n minus 1. Idea is to divide this in even and odd. So, this is called divide and conquer. This is a British rule, recorded. Okay, we divide and rule. So, divide this data into even and odd. So, not divide like left right, okay. So, even and odd, and then again further keep dividing. So, you make like a tree. So, instead of doing this thing with equal, then you say you compute even odd, even odd. So, basically it is dividing in a tree. So, instead of doing it in one way, then you just have to make a tree structure and solve in hierarchically. So, this is one idea which I am trying myself in some different fields. Let me just make a remark. So, this is solving a problem by hierarchy, spelling HEI, hierarchy. So, you do not solve a problem in at equal level. So, the thing is, I would like to say, so you want to solve a country's problem, you do not go to every house and solve the problem. You solve at a multi-scale level. So, you have to make a policy at large, at the country level, then district level, then state, well, village level. So, you have to solve in a multi-step way. So, it is like divide and conquer. You do not do all of it in one shot. It is just too bulky. So, this is the idea. So, divide even odd, and it turns out it is done in n log n, and this is a very powerful idea. Okay. So, this is works even in mathematics. Yeah. So, I do not want to solve, I do not want to sum in one line. So, let us say we have 8 data points. So, 0 to 7, then even will be 0, 2, 4, 8, odd will be 1, 3, 5, 7. Now, this 0 to 4, 8 I can again divide. This something is on. Stop please. Okay, done. 0, 4. So, divide by 2, that becomes 0, 1, 2, 3, 0, 1, 2, no, there is no 8, there is 7, this 6, sorry, 6, there is no 8, no, and this can further be divided into even odd. So, you keep breaking into half each time. So, that is how it is called dividing, and once the data becomes small, then you can do the Fourier transform of the small data, and then you go up. Okay, so, this is, if you look at Wikipedia, you will find the details. Okay. So, anyway, we will not get into this, but this is done in n log n, FFT. So, this is what we need to compute Fk. So, I am computing Fk, okay, given Fj. So, there is another nice property, or well, nice or not nice, but is a property of Fourier transform, which is Fk bar plus n is Fk bar. This property of discrete Fourier transform, DFT. You can easily check, no. So, if I put k bar is by k bar plus n, I get the same thing, because n in n will cancel, and 2 pi ij is exponential is 1. So, this is really important property. So, it is because of this property, it is nice to represent in a circle. These are followed in many textbooks. So, my data is starting from here, and I just put them as points on the circle. Okay. So, my this n by 2, then this n by 2 plus 1, but by using this property, n by 2 plus 1 is, I just subtract n, add or subtract. So, this is, or in fact multiply by any alpha, any integer j. I do not use j let us call it S. S is integer. It works for any of it, right? I mean, you can straightforward check. So, if I subtract n is also, I should get the same transform. So, what if I subtract n, what will I get? Minus n by 2 plus 1. So, these are points, that n points. What is this n minus 1? So, what is that n minus 1? Subtracting is minus 1. So, all the negative ones were up here, all the positive ones are below, if you like, till n by 2. This point is n by 2. So, positive ones from 0 to n by 2 lower half, and above part is negative. Is that clear? But in for solving this problem, it is important, it is sometimes useful to think 0 to n minus 1. Do not think negative positive, but for physics it is important to keep in mind that it is like that, okay? Or we can write like this. This included, square bracket means included, left bracket means not included. Okay, is that clear? So, this notation. Now, I will make life bit difficult for you. So, this is called dealiasing problem. So, what is the problem first? So, there are two functions f g, I multiply, no, I need this real space multiplication. So, this is in real space, f of x, g of x, multiply, then do the Fourier transform. So, my notation is f g k, that means this is the Fourier transform of the product. Now, what will that be? Is a convolution. In 1D, just there is no vector. Now, here my understanding that my k and p is minus infinity to plus infinity. So, this is fine. But when I do discretization, then I do not have minus infinity to plus infinity, I have minus n by 2 plus 1 to n by 2. That is where the problem is. So, my convolution will have error because of discretization. If I had infinite n, then no problem, convolution will be exact, but because of discretization there is a chance of error. And what is the chance of error? Now, so if you recall, so let's just make one line, this p f of q g of p exponential I k plus sorry, if you look at the proof, then it is done like this, p plus q minus k and integral, no, I mean, this is a proof which I did in the class. So, there will be a, when I do the integral, I get a delta function, Kronecker delta function. So, but since my p plus q is, so because of the circular property, p plus q cannot be arbitrarily large. So, k is bound, no, k is bounded between minus n by 2 to plus n by 2. So, this is mod of n. So, when I do the Fourier transform by discrete Fourier transform, this is what I will get. So, k plus q n, so minus k must be 0. So, in the picture it becomes clearer, both p q, well, picture is in the next slide, both p and q are going from minus n by 2 plus 1 to n by 2, and there is a mod here. Okay. So, let me show you the picture, I think picture first, or okay, let us show the picture here. Okay. So, basically I add p and q. So, if this is p, this is q, then p plus q will give you n, k, p plus q will give k. So, these add together, p plus q will lie somewhere here. What if my p plus q is p is here and q is here? It can come somewhere here. So, when you add them, so if it exceeds n, p plus q, look, in fact this is also not a problem. If p q is here, now since I am mod n, if p and q are here, then p plus q can exceed n. and that is not in my computer, that there is no k in my computer. So, take the mod. Okay. Now, this dealiasing is quite easy to see. So, let us go back to old slide. So, minus 1 gives you p plus q is minus 2, right. So, sin x, if I multiply by sin x, I get sin 2x or sin square x cos 2x, no, which gives you cos 2x, which is 1 plus 1 gives you 2. Sin has plus minus 1, so please bear with me on that part. But because of this property, large wave numbers can also give a small wave number. Look, n by 2 minus 1, n by 2 minus 1, add them, you get n minus 2. Remove n, I get minus 2. Because of this property, there is no place to store n minus 2. So, basically, yeah, so these are these are a problem. If I have large wave numbers, I am adding them, but I do not. So, if I have sin 15x, it will give you cos 30x. If 30x there is no place to save, then it is going to come back by this rule. Is that clear? So, this is called aliasing. So, this minus 2 has two possibilities. So, I come with two names. So, one thing is contribution coming from minus 1 and minus 1, other one comes from this contribution. So, to get a wave number 2, I just sin x and sin x I multiply, but somebody tells you that sin 15x and sin 15x multiply get sin 2x, then something is odd, right? Something is wrong. I can't multiply two large sine functions, sin 15x and I get sin 2x, but computer will give you that. That is the problem of DFT because of this rule. This is called aliasing problem. So, this is aliasing. You know, you heard of this word aliasing? Alias? No, you don't heard of alias? Come on, in newspaper, Dawood alias something, no? This. So, his original name is something else, but he comes with another name. Michael Dawood alias something. So, these are two names. These are two names. Is that okay? So, I hope this problem is clear. So, how to solve this problem in a DFT? URF is a Hindi thing, URF in alias. So, the idea is, so look, so in this picture is what I will try to explain. Okay, so I have two wave numbers p and q, add them I get somewhere here. So, they are small numbers, 1 plus 1 gives you 2, no problem, but when it becomes large, then this going around happens. So, if I take some number here n by 2, let us say n by 2 minus 1, n by 2 minus 1, that is what I was taking, no, in my previous table. If I add them, I will get n minus 2, which comes somewhere here, minus 2. So, minus 2 can be obtained by minus 1 plus minus 1 in convolution, or it can also come from here if these modes are non-zero, if they are present. Now, that is a problem. Having two large wave numbers giving you a small wave number is not a desirable thing. Okay. So, what do? I make some of these 0. I demand that, in fact, the demand is, so I am going to make a circle, I couldn't do it in a computer. Only these are non-zero. Let us say that only till m and minus m is non-zero, these are all zeros. All the wave number amplitudes are zeros. So, now if it is 0, then multiply, I will get 0, I will not have this problem. Okay. So, what is the worst scenario? So, look, if I take two large wave numbers, add them, I get large wave number. So, largest wave number here, positive one is what? So, these are negative, okay, the top one negative. What is the largest wave number? M, largest positive. So, m plus m gives you 2m, which is going, so 2m is not positive anymore, because it goes to other side, right. 2m is, look from this picture, 2m is somewhere here, okay, double, add this length, add another length. So, now since it becomes bigger, so my FFT will give you m plus m minus n. Now, this I want it equal to minus m. So, I want to put a condition that I will get, if I add them, I get somewhere here, it's a negative number, but somewhere here. I am going to explain this in a minute, okay. So, this is a condition, and that gives you m is n by 3. So, this I want to make is n by 3. So, let me explain what it means. If I have my wave number somewhere here, then if I add them, I will be, if I lie within this band, lower band, I am fine, because I am going to keep only these wave numbers. So, when I add my k, my result is valid result, there is no aliasing problem. If I have somewhere, my problem is if I have somewhere here, then what happens? If the two of them lying somewhere here, then add them, adding them will give you, it will come somewhere here, but this I am not keeping, I am just throwing it out. So, no problem, you throw it out, throw garbage, your house is safe, no problem. So, you throw that as garbage, but anything if you keep, let us say P and Q are here, so we are lying inside this band, no issues. But if I am here, then of course it will generate a k outside my range, but I will throw it out. Same thing for negative, I have minus 1 and minus 2, I will give you minus 3 as k, no problem, I keep it. If I am come somewhere here, then what happens? In fact, this is big and it comes somewhere here, okay, minus minus becomes big minus, and that is like you add plus n to that, it becomes positive. So, this again I throw. So, throw this part, throw. So, I keep my data from minus n by 3 to n by 3, then I am safe. So, but my discrete transform must be applied on solver with n, not with n by 3, 2n by 3. So, I should do the function with takes n points, but I have a lot of points set as 0. It affects the solution which I am going to throw, okay. Yes, in some sense. So, the idea is the following, okay. I have f of k, full f of k, set, keep only 2n by 3, only in this red region, throw out other things. Now, from this you construct a real space. From here I can construct f of x and g of x, multiply, then again do the transform, but you keep only the data up to minus n by 3 to n by 3, that is the reliable data. There will be data generated here, okay. There will be, when I do the transform, if I take f g x, I do the transform, I will get k, non-zero k is here, I mean for these k's I will get non-zero amplitudes, but I do not keep it, truncating it, and this called. So, I solve the aliasing problem by this scheme, by 2 by 3 scheme. So, this is called 2 by 3 rule. Total number of points you keep is 2n by 3, and this is called de-aliasing by 2 by 3 rule, okay. So, it is a nice trick. If you want exact solutions, I mean your data is only reliable in this band, the red band, not in the green band. So, this is the reliable data. Well, I made it green, so red band, okay, this region. So, just to summarize, so we keep this data only here. And these are zeros. Before the before you go into real space, multiply, and after the data is done, you again throw them out. Okay. In our code, we keep this data though after the transform. These numbers are small typically, because large wave numbers, the amplitudes are small. They are not correct, not accurate, but we keep the data for spectrum calculations. So, it gives a bigger range. So, we do not, so we are, so this data is of course reliable in our simulation, but we still keep the data for some computations. Okay, but this is a side remark, don't worry. Okay, thank you.